Thank you. Now we have the pleasure to have with us Professor Nicolas Pepas, that is also going to be nominated as academician member of the Royal Academy of Farmacia, Nacional, always forget that, of Farmacia of Spain. And it is a very big honor for us that you accepted. And Professor Maria Vallet is going to introduce you. Professor Maria Vallet.
Excelentísima señora Presidente de la Real Academia Nacional de Farmacia, excelentísimas señoras y excelentísimos señores académicos, señoras y señores, amigos todos. Allow me to introduce Professor Nicolas Pepas, Director of Center of Biomaterials, Drug Delivery, Biotechnology and Molecular Recognition at University of Texas. I am truly honored by this opportunity. I met Professor Pepas in person during a series of lectures that he imparted at my institution, Facultad de Farmacia, at Universidad Complutense in March 2001. All members of my research group attended his lecture, and I must point out that Professor Pepas was extremely helpful and kind with all our questions regarding drug delivery systems. His guidance and advice was also excellent, and I will be always grateful and indebted to him by helping us so much at our first steps in this field. I also extremely satisfied by his appointment today as foreign corresponding academician of this institution. I will briefly mention some Professor Pepas' career highlights. Dr. Pepas is one of the foremost pioneers in drug delivery research, and his contribution to science, both through research and mentorship students, have and continue to improve life for many. As a leader of biomaterials, drug delivery, and pharmaceutical bioengineering, Pepas' research blends modern molecular and cellular biology with engineering to create innovative medical systems and devices for patient treatment. He joined the University of Texas at Austin in 2003 as the Fletcher Stuckey Park Chair in Engineering and Professor of Biomedical Engineering, Chemical Engineering and Pharmacy. Since 2009, Pepas has served as Chair of Department of Biomedical Engineering. Pepas has received numerous academic distinctions from Academic Institute of Medical and Biological Engineering, the American Institute of Chemical Engineering, the Society of Biomaterials, and the Control Release Society, among many others. He is a member of several institutions and academics such as U.S. Academy of Medicine, the U.S. National Academy of Engineering, and the National Academy of Pharmacy. His research interests are focused in biomaterials, polymer physics, drug delivery, and biotechnology from a multidisciplinary angle. He has set the standards in drug delivery systems for the past 40 years. He has been recognized with numerous awards from societies and institutions of biomaterials, medicine, and science. He is a fellow of the American Chemical Society, the Material Research Society, and the American Association of the Advance of Science, among many others. He has published 1,100 papers, has 45 patents, and he has supervised the research of numerous postdoctoral and graduate students. He also holds honorary doctorates from University of Ghent, Belgium, University of Parma, Italy, and the University of Athens, Greece. Dear Professor Pepas, it's a great honor and privilege to introduce you as foreign academician of this institution. I wish you the best luck in your new responsibility.
Professor Pepas is going to pronounce his lecture entitled Advances in Intelligent and Recognitive Hydrogels for Treatment of Diabetes, Cancer, and Multiple Sclerosis.
Madam President of Real Academia Nacional de Farmacia, academicians, dear colleagues, ladies and gentlemen, it is a great pleasure for me to be here today, and I want to thank the Academy for this great honor and great recognition, and I want to thank my many friends in Spain for really giving me the opportunity to present again, and to thank all of them for really the great collaboration and work we have done together. For me, this recognition is really very, very important to be in this great building, to recognize a section of the Academy of the Institutos de España, an academy that was created in the 1750s by Felipe V, and which is in its present reincarnation since the 1930s, has been really promoting pharmacy. I will have the opportunity to make some remarks at the end of my talk about my interactions with Spain. But I do want to start first by talking about advances in a subject that is very dear to me, and that is that of treatment of patients using new types of delivery systems. The symposium is Drugs, Nanomedicine, and Biomaterials. Why biomaterials? Why nanomedicine? Why now? Because if you really look at the pharmaceutical world, you're going to see that we live in a very difficult period. It was 50 years ago that Takehiguchi, a Japanese who was born in the United States and who was interned in World War II because he was considered to be an enemy of the country. That man, after World War II, became really the leader of drug delivery, and in 1961 published a seminal paper that anybody in the audience knows, the Higuchi equation, the equation with which we first designed new drug delivery systems. It's an equation that is very simple. It says that the drug delivery rate is proportional to the square root of time for the early part, at least, of a release process. But it was very interesting that when it first came up, it gave us the opportunity to understand how to analyze such systems and to design some systems. Since then, there have been the advent of drug delivery and of course, control release. But the signs that we have today are not very good. In 2006, Pfizer, Sanofi Aventis, and Nectar introduced a pulmonary delivery system for treatment of diabetic patients, the Exubera system. The system was supposed to have a $2.5 billion market the first year it was introduced. It was a relatively simple system. It was going to be a pulmonary delivery system with a little applicator that the patient would take discreetly out of his or her pocket and use it 2 or 3 times a day to get insulin. The system was called Exubera. 1 year after introduction, in October of 2007, the system was withdrawn from the market, and Pfizer took a $2.8 billion, not million, billion dollar loss, and the system does not exist anymore in the market. Now, there are many reasons why the Exubera system failed, but at the same time, at least in the United States, and I don't know if the same thing happens in Spain, when you go now to what we call a pharmacy, which is slightly less controlled than your pharmacies, what we see is the announcement, for $4 a week, you have all the medicines you need. And then you have companies like Walgreens, which is still a pharmacy-based company, and Walmart, which has nothing to do with pharmacy, fighting for who is going to give less expensive products in the market for the patients who cannot afford to pay for the ethical pharmaceutical product. So generic products have become very important. I'd like to submit to all of you, how are companies like Pfizer and Eli Lilly and Merck going to survive if we as consumers want to spend $4 a week for our medicines? Who is going to pay for the new research? And yet something happens in the field, and there are some positive signs. Because all of us who analyze the field, and Ruth had said it very nicely, we see that there is promise. We do have new systems for targeting of novel medical treatments. We have protein delivery to patients. We have new systems that are available. Intracellular delivery, biotechnology are becoming very important, and more systems which diagnose, recognize the undesirable compound that is responsible for a particular disease, and they start treating that disease. And on top of that, I would like to add something that Professor Duncan so nicely presented in her talk. We are all concerned about the third world. We are all concerned about how we can translate all these products into products that can be affordable to Africa. Do you realize that in Malawi, the annual budget per patient for medical health is $17? Do you realize that in Lesotho it is $12? Do you realize that in Lesotho 37% of the population have HIV? So we really have some serious problems, and it is a mistake for all of us to think that the problems are third world problems. They are not. They are problems for the United States, for Canada, for Japan, for Spain, for the United Kingdom, and so on. There is an internationality, but at the same time there is an effort to cut down costs, to miniaturize devices, to be able to make the devices easier to use. And that's why more and more of us are talking about portable devices. And that's why Ruth so nicely at the beginning of this talk of this morning, and Sam after me, are going to be giving us really examples of nanomedicine as applied to our field. But there is a certain internationality, Madam President. And the internationality is that all three recipients of this great recognition today were educated as non-pharmacists. One was educated as a chemist and material scientist, one is a biologist, and one is an engineer. And isn't it also whimsical that although we work right now in the United Kingdom and in the United States, one of us was born in Greece, one was born in Scotland, and one was born in Costa Rica. And so that shows you the internationality of this particular field. And one shows you what we try to do. There are no barriers. There are no limits. We are all trying to work for the common good. And at this point, I would like to give one or two of my heroes of pharmaceutical biotechnology. And one for me is Professor Peter Speiser, that you see on the upper right side, who was professor at ETH in Zurich for many, many years, and who has been succeeded by some of the major leaders that you see down there. From the very left, Bob Davis, in the middle, Robert Gurney, under him, Jörg Kreuter, Patrick Couvreur, and Thomas Kissel. And of course, Jan Fayen is not in the same tree. Jan Fayen is the major professor of Wim Hennig that you saw yesterday. You can see how the work comes together. And if you look at the publications in nanotechnology, you're going to see that it was in 1976 that Peter Speiser published the first paper with that word in mind. And it was only in the 90s, in the year 2000, that we started having an explosion in the field. And today we have a totally new world. Well, everybody's talking about nanoparticles for drug delivery. You've seen it over the last 2 days, but I'd like to specially give a recognition to some of the true giants of the field. From the upper left side, two compatriots, Greg Gregoriadis, upper left, and under him, Dimitri Papahajopoulos, who was lost tragically a few years ago. And to the right, Frank Zoka, who continues being one of the main leaders in liposomes. On the very right side, the dendrimers, Jean Franchet, many of you know him. He decided to spend now a new life in Saudi Arabia, who was president of a major university in Saudi Arabia, and above him, Don Tomalia. And of course, my idol, Ruth Duncan, whom I remember as a postdoctoral student in the Control Release Society when I was an associate professor or even full professor, and then a wonderful work in the field. And of course, Professor Kataoka and Professor Patrick Couvreur, another one of the young colleagues that really did wonderful work in the field. We are all addressing the question of nano-delivery of drugs. And we are hoping that someday these structures that I show here in a recent paper from Nano Today will be used for diagnosis and delivery, not just for delivery. So we will have an imaging system that will fulfill perhaps someday the goals of Paul Ehrlich and the goals of Fisher, Emil Fisher, who were really the ones who were looking at recognition and delivery and treatment of diseases. And that's going to be possible by stimuli-responsive networks. This is from a recent paper by Merical Dorera Moore, one of my postdocs, in which we show how we can use pH sensitivity, temperature sensitivity, or analyte sensitivity to treat diseases. Can you imagine if someday we will be able to recognize glucose and treat diabetes? We will be able to recognize angiotensin II at high levels and treat high blood pressure, and so on and so on. Because the problems we are addressing are world problems, and they have the potential to become true world epidemics. This is from the PhD thesis of one of my students, Irma Sanchez, who is now professor at Tecnológico de Monterrey in Mexico, and who has compiled this data that show that by the year 2025, this is going to be the estimate of how many people are going to have diabetes in the world. And that is both types of diabetes, type 1 and type 2. So diabetes is becoming an epidemic, and wherever you see dark lines, you realize that we're going to have a serious problem. And it's not only a problem of obesity. In the United States, it's a huge problem of obesity. You live in Europe and you haven't really worked in an environment where people come around carrying their own oxygen tanks and being truly obese and not being able to sit in a regular chair anymore. And yet, these are people we have to treat. These are people that we cannot abandon because we are pharmacists, because we are biomedical engineers, because we are biologists, because our foremost goal in life is to improve the quality of life of those patients, whether it's by prevention and education or by treatment. What I have done in the last 12 years, since about approximately 1999, but definitely after I went to the University of Texas in 2002, is to concentrate on transmucosal delivery of proteins. And I have worked with a number of proteins where I have tried to use my background as a polymer scientist, as a biomaterial scientist, to bring together a good understanding of biology, but at the same time, good understanding of delivery processes to come up with new systems for transmucosal and especially oral delivery of proteins. And as you can see, the applications that we have are in a variety of areas. I'm not going to talk about all of them today, but there are now calcitonin delivery systems for postmenopausal treatment of osteoporosis, growth hormone systems for delivery for dwarfism, interferon beta, about which I want to talk in a few minutes, for treatment of multiple sclerosis, and our latest work with my wife, Lisa Brannon-Pepas, on the treatment of hemophilia orally using factors 8 and 9, which is a revolutionary new way that will change the way little kids are presently treated for this particular disease. But today I want to concentrate a little bit more on insulin and interferon beta, and if I have time, a little bit on cancer. You all know the structure of insulin, and you know that you cannot take it orally. Insulin is going to denature immediately. The actual bioavailability reported for direct insulin oral absorption is going to be of the order of 0.01%. So we have to find ways to protect insulin if we were to deliver it orally in the upper small intestine. And as I will show you in a little while, that has become possible now. 15 years ago, I remember a congress in Copenhagen in August of 1997 by the Benson Foundation, in which major researchers in the field were saying it will not be possible to deliver proteins orally. I'm not going to mention who these individuals are, but I'm going to say that when you try and you come up with a new solution, someday you will succeed. Calcitonin is another molecule. If you start looking at the structure of calcitonin, you see one big difference, which is the isoelectric point is 8.6 versus a 4.4 for the case of insulin. So what we are developing here is not a platform that will apply to each and every protein, but a system that can be modified depending on the protein we are using. At this point, and since I know that I have in the audience quite a few polymer scientists, and since the title of the session is also biomaterials, I will turn a little bit towards the materials aspects. What are we looking for here? We're looking for a microparticulate system or a nanoparticulate system that somehow will bypass the stomach, arrive in the upper small intestine, stay in the upper small intestine for a period of time, start delivering the insulin. I'm going to be talking about diabetes. And that insulin somehow, by a magic way, will pass in between the epithelial cells and get into the blood and act in the blood. And will do that at a relatively high rate. Because we are scientists, but we are at the same time businessmen, whether we like it or not. And we cannot just develop a product and hope that Eli Lilly and Pfizer will accept it. If that product doesn't have a good bioavailability, no chief financial officer of any major company is going to accept it. You cannot convince the chief financial officer of Eli Lilly that something that delivers only 5% insulin will be placed in the market. So right from the beginning, you have to have a good understanding of the passage through the epithelial cells into the blood. Now, for those of you who have a rudimentary knowledge of engineering, you will see that this is a fluid mechanics problem. The particles are kept next to the mucosa. They move originally with a Stokes-Einstein type of equation, where you can see the diffusion coefficient is inversely proportional to the size of the particles. Eventually, they will stay in the mucosa and they will start releasing. We have developed one such system which protects the protein from degradation. It's an anionic complexation hydrogel. It releases the protein at specific sites, and that is done by pH-responsive behavior. It improves the residence time because it has tethers, and those tethers act as adhesive characteristics, as adhesive anchors. It's like having molecular anchors that come out and they attack the system. And finally, it starts releasing and improves the permeability. And this system is the polymethacrylic acid-based system with polyethylene glycol chains that we know they form hydrogen bonds, and therefore they expand and contract depending on what pH you are. I have mostly pharmacists in the audience. I don't need to remind you that the pH as you enter the stomach after the esophagus is about 1.6, 1.8, 2, unless you ate a pizza last night and it was extremely acidic. And it continues going down to 3, 4, 5, 6, and the pylorus is about 6.7. And then we enter the upper small intestine, 6.8, 6.9, all the way down to the colon where it's going to be about 7.8. These systems have the ability to be triggered. You break the hydrogen bonds, you open up the structure, and the protein starts releasing. Look at the complexation as a function of pH, and you can see at the low pHs the complexation is very high. The system is complex. It does not allow the protein to come out. Notice that when you have at a pH of 6.5, there's total decomplexation, and indeed the protein can start releasing. This is my view of how this process takes place. Notice the system is not biodegradable. It doesn't have to be biodegradable. The system works in the upper small intestine, and eventually what is left will disappear the natural way. Therefore, you don't need to spend extra attention to come up with a biodegradable system for this application. This is a very nice analysis for those of you who understand polymer science. What we have done now here is a small deformation experiment where we take some of these gels with the hydrogen bonds and we test them on an instron and we measure the stress. That tau is in pascals on the left side, as a function of alpha minus 1 over alpha squared, where alpha is the elongation. You know that the Flory theory says, or the Mooney-Rivlin theory says, that you will have a straight line at very small deformations, and indeed you have that straight line. And notice something else. As you increase the pH from 3.5 to 6.8, you see that the slope goes down. The modulus goes down, which means the material becomes softer and softer, less strong. This is an indication that you have opening of the effective crosslinks of the system, and therefore eventually that will be released. And indeed, I can show you this diagram, which is the result of a lot of calculations and studies, and it shows you the mesh size at a pH of about 4, 4.5, very collapsed, and the expanded one at about a pH 7, 7.8, You can see it's opened so the protein can start delivering. Now, some of them are going to say, yes, but the change is only from about 70 angstrom to about 210 angstrom. That's 3 times. Is that enough for a fast delivery of the drug? Because I would like to have insulin deliver as soon as I hit the upper small intestine. Otherwise, I'm going to have other side effects. Never be deceived. The scale up in the body is not according to the linear parameters. Nature does not understand what a straight line is. So if you really do the calculations, the exact ratio of the diffusion coefficient of insulin at a 6.8 over 1.2 is 550 times higher. So although you have 3 times higher, larger mass size, you have 550 times higher diffusion coefficient. And this shows you that the system really acts as an on-off switch. These are some in vitro studies that show you that if you are working in a simulated gastric fluid at 1.2, you have very low release of the insulin, yet you pass at a 6.8 and you have a very high release. But that doesn't mean anything. That simply says that the drug is going to be releasing at a high pH. What's going to happen after that? Well, these systems have several unusual characteristics. One I would like to describe here because it's a very interesting phenomenon and it relates to one of the heroes that Ruth Duncan described a few minutes ago. The phenomenon is mucoadhesion. This system contains these green lines, which are the polyethylene glycols, which, however, at a pH of 6.8, have a tendency to open up because you break the hydrogen bonds. And so you have free polyethylene glycol chains, which now have a tendency to start interacting with the mucosa. Don't forget, polyethylene glycol is to some extent compatible with the mucosal characteristics. And the result is this type of interaction, localization, because of these chains come in contact with the microvilli and the submucosa, and they start penetrating in the submucosa. We treated this phenomenon for the first time about 26 years ago. I was working for Sandoz at that time in Basel. I was on sabbatical, actually 28 years ago. I was on sabbatical at the University of Geneva working with Pierre Bury, and we published this paper in which we analyzed the molecular aspects of how mucoadhesion and bioadhesion takes place. And then a few years later, I remembered something that Pierre-Gilles de Gennes had said. De Gennes had said that macromolecular chains have the ability to penetrate. In fact, he said that they could interdigitate. There's a famous paper by de Gennes and Brochard, perhaps you remember it, in which this interdigitation took place. And we started working with that process of interdigitation. And we said, if a control release gel system, red, is in contact with mucosa, green, and you bring them together and you have compatibility, slowly there will be interdiffusion, and effectively that interface will disappear. And indeed, that's what happens. So in many of the systems that I showed you with the polyethylene glycol, what we have is the polyethylene glycol penetrates inside the mucosa. And the result is the formation of these structures. And the question is now, do I need large molecular weight pegs and a lot of them? Or what will be the surface coverage? And this is the phenomenon we have started analyzing. It was done in the last few years in a very nice way, and most of these papers were published in biomaterials or polymer journals, looking at the dynamics of surface decoration and how the polyethylene glycols and other structures can be placed on top of these particles. And one of the things we found out is that if you have too long polyethylene glycols and too many next to each other, guess what? Some of them don't contribute to the adhesion because they collapse, they become like mushrooms, and they stay very close to the surface. So there is only an optimal coverage of the surface decoration at which you can achieve this type of adhesion. And this is a very nice mathematical analysis that was done by Yanbing Huang and me. Yanbing is now a professor at Tsinghua University in China. And we were able to show, as you go to the right side, that there is penetration at certain coverage lengths, penetration inside the mucosal gel. Now, that's very good. So we understand some of the molecular aspects. But let's talk a little bit about some results. And these are probably the earliest results you have seen in the literature on oral delivery of insulin using this type of systems. Please notice that we have the serum glucose as a function of time for diabetic male Wistar rats. They were becoming diabetic by pancreatomization. And you can see that the glucose concentration starts dropping and kept staying low for about 8 hours. Now, these studies were done with animals and with concentrations that were such as to scale up into human. And the earliest studies were done in collaboration with Professor Nagai and Professor Morashita at Hoshi University. But how exactly does this process take place? The particles come into the surface, they attach to the mucosa, they start releasing the protein passes in between the epithelial cells or through the epithelial cells and gets into the blood. What types of mechanisms take place there? Passive transport? Most probably not. Insulin cannot be transported through cells under those conditions. Convection is a possibility. Cell permeation might be a possibility. Binding, of course, takes place, and transcytosis takes place. So we started working on trying to understand these pathways. And what we realized very early was that one pathway of interest was number one, paracellular pathway. What does this mean? It means somehow the polymer particles open up the tight junctions and they allow the transport of the protein through them. And then, of course, the tight junctions close again. I would like to remind you that tight junctions have a size of about 1.5 nanometers. So very small. If you open it up. The other thing, however, you cannot open it up for too long, because if you open it up for too long, then you may have viruses penetrating in between the cells, and you may have some other problems while you are treating a disease. The other major parameter, mechanism that is quite interesting is 2A or 2C, carrier-mediated transfer. And that translates to something I'm going to say in a little while, transferring, binding, and conjugation. So we started working with all these things, and this is where we applied our engineering. We came up with mathematical modelings. The reason was because we wanted to identify which parameters could be modified so that we could increase the transport of the protein across the epithelial cells into the blood. And the nice thing about these models is that we know all these parameters. We know the values of the various parameters that appear, such as the diffusion coefficient of the protein, the velocity across the cells, the permeability, and so on. And I'll show you just one result that shows you what you can do with engineering to solve a pharmaceutical problem. Here's the concentration as a function of position inside the cells. And it shows you what will happen if you go from a diffusion coefficient of 10 to the minus 9 centimeters squared per second to 10 to the minus 11 centimeters squared per second. 10 to the minus 11 will be a large protein, 10 to the minus 9 will be a smaller protein. And so you start understanding the barriers to the transport of that protein and the passage to the blood. So what is the goal here? To increase bioavailability. How can we increase the transport across the epithelial cells in the blood? And we started working, like a few others, with decoration of the surfaces of our nanoparticles by the addition of tethers. And of course, the first tether we were using was polyethylene glycol, but then it became obvious in some of your more recent work that we could replace polyethylene glycol with some other compounds that have the ability to promote transport, such as certain types of carbohydrates. And with Maggie Phillips, who just finished her PhD, we started working now with tethers, which are large carbohydrates. And this is where we have been very much inspired and also taught a lot by Wim Henning and his wonderful work on the field. We started working by adding dextrans or by adding pollulants, which now have the ability to interact with cells. Most of this work has not been published. But the reason we work with these polysaccharides is because it has been shown in other studies that they contribute in adhesive processes. So we thought we were going to have our particles now for a longer period of time in the upper small intestine. And this is really what we did. This is one of the relevant papers you might want to see, in which we functionalized the polyethylene glycol through a well-known technique using the hydroxycinamide compound, and we were able to add now on the surface carbohydrates. Having these carbohydrates, we were able to study the swelling and release behavior, which is quite similar to that of the original materials, as you can see here, very small changes. But the most important thing is an improvement in protein incorporation now. We are able to have loading of about 55% in calcitonin, about 85% for insulin, about 75% for interferon beta. Please remember this molecule. I'm going to come back to that molecule. So these are some results now with a particular structure where we have added at the end a certain tether. The tether in this particular case is a lectin, a WGA lectin, and you can see because of the addition of the lectin, we have now much higher ability to interact with the surface of the mucus, and this is porcine gastric mucus, and you can see we have the ability to keep the particles for a much longer period of time there. And now we are coming to the actual transport studies, because don't forget, regardless of what we see with animals, what we really want to do is improve the bioavailability. So we use Keiko-2 cells, like many others do, and we use them usually at a certain passage of about 65 to 75. We like them because they form tight junctions, they produce enzymes, they develop microvilli. They have one disadvantage: they don't produce mucus. And at the beginning, hard-headed as I am, being a Greek originally, I said, nah, we will still do the study that way. But you know something? When the National Institute of Health says, we're not going to give you any more money to do work unless you have also something that produces mucus, then you listen. So we came to France and we found Dr. Thecla Lesouffleur, who is at INSERM at the Hôpital de Bray in Paris, and she helped us very much. She gave us the HT29 MTX cells, which produce mucus. Then we mixed them with the Keiko-2 cells and we created a co-culture, and that co-culture is now what we are using as a simulating system to really see what happens in the real system. And we do typical studies that most of you are familiar with. We use a 96 well plate, we use a transwell cell, and we do, the first experiment we do is a toxicity experiment in which we measure the metabolic activity in cells. And I want to show you the results of that for the Keiko-2 cells on the left side, for the HT29 MTX cells on the right side. Look at the data, you see are at about 100% viability. In principle, these structures do not kill the cells. The error is a reasonable error for those techniques, and we've checked it with Per Arthurson at Uppsala and other investigators who work in the same systems. It seems to be a little bit large, but we are at 100% viability. And then we do the transepithelial resistance test, in which we take a transwell, we put a polycarbonate film, on top of that we put the cells, the co-culture, and we allow them to form tight junctions, and then we start doing an experiment with our system, with the insulin, where we go from the apical to the basolateral side. And we measure the resistance. If the resistance is constant, that means nothing has happened to the system. If it decreases, that means we have passage of the protein through the system. And here are some results with Keiko-2 cells and with the co-culture on the right side. You can see slowly the resistance goes down. If I showed you these results over several hours, you would see that they come back to the original value. We can actually calculate the insulin permeability from these studies. And what we find is that the insulin permeability is about 20 times higher in these systems that we have developed over what you would have if you have simply an insulin solution. So these studies are really exciting, but let's look at some of the animal studies. So these are studies now that were done more recently in collaboration with the Thomas Jefferson Medical Center in Philadelphia, our collaborators there. And I'll show you on the left side results where you take now these particles, you put them in a microcapsule, you give them to the animal, they pass to the stomach and the upper small intestine, then the capsule breaks and the particles find themselves and the process starts. Look on the right side. Look at the red line, which is the one that contains the lectin. You see the concentration of glucose goes down, and this is a very interesting result. But if you are a pharmaceutical scientist in the audience, you say, what is the etiology? That's not enough for me. Is the insulin in the blood? So you look on the left side and you see after about 15 minutes, insulin is already in the blood. And it remains in the blood for a reasonable time. And you know that you can take the area under the peak and calculate from that the pharmacological bioavailability of the system. At the same time, we did biodistribution studies. And actually, that's incorrect. They were published. If you look at Mariko Morashita's as first author, they were published this year. And you can see that indeed the particles stick mostly in the upper small intestine, very little in the middle and the lower small intestine, and most of the release takes place in the upper small intestine. So really we have a system that can deliver its protein at a specific site over the desirable period of time. And then comes the little gift. And I know that I'm a scientist, but still for me that's a gift. I never expected any inhibitory effect of these particles on the proteolytic activity of enzymes in the stomach and the upper small intestine, and then we got it. We clearly show here that we have the ability to protect the protein, insulin in this case, over a long period of time. And we still don't understand 100% why that happens, although we have interactions with Klaus Micheler at Saarbrücken, who shows that if you have a structure with a carboxyl group, you protect, you avoid proteolytic activity in the upper small intestine. So that's very interesting, but this was the result from this study. Now, something else that has become very important for us is to try to see if we can use transcellular mechanisms. And one of the transcellular mechanisms is transferrin. Can we combine as a conjugate transferrin with insulin to create a structure that we believe might have a much better permeability across the epithelial cells? And I want to remind you again, passive transport will not occur with insulin. Efflux transport will occur, and you can avoid it sometimes. This is what we want to achieve, carrier-mediated transport, or why not also receptor-mediated transcytosis. And so what we did is we did a reaction in which we conjugated transferrin with insulin, creating a much larger molecule, yet one that surprisingly enough has a better permeability through the system. This is my rendition of how I think it's happening. It's taking place. The capsule gets in the stomach. There cannot be diffusion out because you're not at the right pH. But when it gets in the upper small intestine, the capsule breaks, there is diffusion out, and now you have the conjugate, passes through the system, gets to the other side. And if you don't believe me, let me show you some results with cells, same cells as before, for the transport. And you can see the polymer conjugate has a permeability of 24 times 10 to the minus 9 centimeters per second, whereas the control is at about 1 times 10 to the minus 9. So clearly we have a significant transport through these systems, and we are working right now much more to understand that system. Ladies and gentlemen, this is the direction that my laboratory has been taking in this field. I'm working with medical doctors right now to try to give a better answer for the case of hemophilia. But I'd like to talk to you for a moment about something very personal. It was in March 2001. I was here on sabbatical at Complutense University with Professor Juan José Dorado and his colleagues. And the agreement was I was going to be teaching and doing research the week, except that Juan José was going to ask people to invite me for a seminar in a different department every Friday. And so that's how I met everybody in pharmacy in Spain, going from Tenerife to Barcelona and from Sevilla to Santiago de Compostela. And it was in a meeting in Barcelona on a Friday afternoon that what do we call the expression? I came out and I told people, you know something? I have multiple sclerosis. And people were shocked. There were a lot of undergraduates in the audience. In December of 1994, I was diagnosed with multiple sclerosis. And the first thing you do when that happens is you cry. Then you realize your life has changed. You realize that in a few years later you're going to be in a wheelchair or with a cane, and you will never be able to walk again. and you tell your wife, you don't need to be with an invalid, I will divorce you. And she says, you're crazy, that's not what marriage is all about. And then you say, we're going to sell our 3-floor house and we're going to live in a ranch house, means 1 floor. And then you start taking the drug. And the drug was interferon beta, and still is interferon beta, which at that time was formulated to be used once a week by intramuscular injection. How many of you have had intramuscular injections? Do you like them very much? It's a needle about yay long, going straight down, here, there, up here. Listen, in my case, I could never do it up here, because I was always afraid that the needle was going to hit my bone and break inside my bone, and I didn't want that. So you take it, and then your old pharmacist, the first 48 hours, the concentration is very high. You have a very potent drug. You have all kinds of side effects. They suggest that you take Tylenol and so on. And you go to Biogen or Merck Serono, and you say, please come up with something better. And they say, no, that's fine. It works very well. What they don't realize is that if you're doing intramuscular injections, after a few weeks, you have developed scar tissue in here and there. And now the next time you try to do an intramuscular injection, you hurt. So I said all these things in Barcelona, and as a result of that, I started a wonderful interaction with Barcelona and also with some students who came and worked with me in the United States. Ladies and gentlemen, I know how to do injections to apples and oranges and pears. But when it comes to me, I cannot do it. Somebody else has to do it to me. And my wife was doing that once a week. And Juan José Torrado remembers that every Thursday we would visit somewhere in Complutense to have the weekly injection. And of course try to convince the TSA, which is the United States Equivalent of Security, try to convince them that you're going to Europe and you're carrying with you a syringe. And that this syringe is for personal purposes. You're not going to attack the pilot with it. And try to tell them that you should put it in the refrigerator to use it later. None of this happens. So please, Merck Serono and Biogen, don't tell me that there is no problem. Comes back to what Ruth said. Improve the quality of life of our patients. Don't have them stay in bed because they are taking interferon beta. We are working with Toray Industries and with Mariko Morashita. These are the first results we have published. We published them about 1.5 years ago. They have already received hundreds of citations. This is oral delivery of interferon beta for the treatment of multiple sclerotic patients. And I want to tell you, the people from Toray will be very, very bold and brave if they decide to put this product in the market someday, because the bioavailability is only about 10%. And the typical payment that I was paying in the United States for the Avonex product was $350. So you can imagine now, you're a chief financial officer of a company. You decide how you're going to use an oral delivery system that is better to the patient, but loses about $300 each time you do this process. I don't want to keep you waiting. 10 years after I was diagnosed, nothing had happened to me, and at that time it was discovered that I did not have multiple sclerosis. I had been misdiagnosed. I have another disease. It's an autoimmune disease, but it is one that can be controlled. I always believed that there was divine intervention, that it happened to me, because without it I wouldn't be working on interferon beta. I don't have time to tell you about the third major contribution, which is in cancer. It's really a wonderful work that we are doing with the Methodist Hospital and with Rice University and Harvard on oral chemotherapy. But in view of the time limitations, I do want to spend 1 or 2 minutes talking about Spain and my interactions with them. And so, before I get into the final comments, I want to say we're very happy with what we are doing in the field. We are working with a number of companies. We are trying to put one of these products in the market, and the data are reasonably promising. But of course, there are many more studies that have to be done. but suffice it to say, both my students and I are passionate about improving the quality of life of our patients. And I'm thankful to the Real Academia Nacional de Farmacia for this great honor today. This is very important for me, important because I was born and raised in Europe, and I left 41 years ago. Important because this is Spain. My first interaction with Spain, of course, was with Cervantes and Lope de Vega. But it became, after that, many other things. Probably I'm the only one in the audience who has seen something related very much to Spain that the rest of you have not seen. On May 14th, 1962, I was in Athens, a 13-year-old, holding a Spanish flag and a Greek flag and participating in the wedding of Doña Sofia with Don Juan Carlos. They were both very young, and I want to tell you, regardless of what you may have heard about the Greek kings, and probably most of it is correct, Doña Sofia was always the beloved princess. So people may not like as much the rest of the family anymore, but they still love Doña Sofia, and that explains to you why she still goes back to Greece from time to time. And this is a newspaper on May 15th showing there is one more person in the audience who can read Greek. There took place yesterday the weddings of Sofia with Don Juan Carlos. 50 years ago this month. And then I want to say that my interactions with Spain have been incredible. José Luis Villajato was, for me, almost contemporary, was a man that was really helping me whenever I was coming to Spain. And as you heard at the beginning of this presentation, he was the one who did the original nomination for me at Santiago de Compostela. He died last year, and he will be sorely missed. Tomorrow night at the Academy at 7 o'clock, we have a memorial, his memory. And of course, Maria José Alonso on the left. I met Maria José in 1985 in Paris Sud, in the laboratory of Patrick Couvreur. She was a postdoc. At that time, we knew her as Marie-José. That was her French name. And over the years, we became extremely good friends and interacted a lot. And on the right side, you would see Loli Torres. Both of them are at the University of Santiago de Compostela. And this is another picture with Patrick Couvreur, with whom Maria José was working at that time, and Jean-Pierre Benoit. And this is a picture to which related to a meeting to which Ruth Duncan alluded, and that is the first Luso-Ibero meeting of CRS, Control Relief Society. I had the idea for us to organize a symposium here and the society here, and that started in 1995. It was at Santiago de Compostela, and you can see Maria José Alonso, Professor Villajato, Professor Torres, and many other Europeans, including Rogerio Gaspar on the very left, who, although Portuguese, was always very close to the community, the Spanish community, and always helpful. And on the very right, a younger Nicolas Pepas that you will not recognize now. And this is another one of my big Spanish loves, if I may use that name, Carmen. This is Carmen Alvarez Lorenzo with Ángel Concheiro, two leading authorities in molecular imprinting. Carmen Alvarez was the last PhD student of postdoctoral of Professor Tanaka at MIT before he died, and she has done absolutely wonderful work in the field of molecular imprinting, and she's in the audience today. I like to put people in difficult positions. And Julio San Roman, with whom we have worked a lot together, and Carmen Mijangos, with whom we worked more recently. We have at least one paper published in Soft Matter, and you will see why. Two great scientists in polymer science. And of course, Maria Vallée, who I thank very much for the invitation and the nomination, and with whom I met for the first time in 2001, as you heard when I was here on sabbatical. And these are my friends at the University of Barcelona. Yes, you can be in Madrid, but you still like the people from Barcelona. They are nice people. In fact, I have Catalans in my laboratory, especially Professor Joseph Domenech, with whom we did a lot of wonderful work in bioadhesion, and Professor Pereira and Ana Calpena on the right side. And here, of course, the three Dorados with whom I have kept a very good relation, Santiago, Susana, and Juan Jose, who is now the president of the department at Complutense, and Professor Lastres, who has retired. And finally, from a recent PhD thesis with Marta Gomez, which brings me to the end of my talk and the contributions of the students. I've had 7 PhDs or postdocs from Spain. I have pictures of 6 of them. The 7th one, not yet a picture, she's relatively new. This is Marcos Garcia Fuentes at the University of Santiago de Compostela. He was in my laboratory 13 years ago. He's doing very well right now. Laura Serra from the University of Barcelona, she was the young lady in the audience the day that I announced that I had multiple sclerosis, decided to come and do her PhD with me, and she did all the PhD in the United States. Marta Gomez, I think she's in the audience, and if she's not, she will be soon. Got her PhD from Complutense after having come to Texas and worked with me. Coro Echeverria, I know she's over there on the 4th row, worked with Carmen Mijagos and me and has just finished her PhD. Ana Fernandez Olleros is still with us. She's somewhere in the back doing her PhD with Professor Blanco and me. And Edgar Perez Herrero, the only engineer from the University of Salamanca, who is now back to Salamanca as a professor, assistant professor of chemical engineering. The 7th one is Mark Reichel from Barcelona, and now in my group as a postdoc. This is my group at present time. As you can see, in the United States, biomedical engineering is a subject for women, and I'm delighted that I am encircled by women and young people. It makes me feel young. And I want to close with a picture from Austin. It's a nice, beautiful city, and the university, on certain cases, is #1 in the country. Thank you very much. Thank you for the honor.